It's Sunday. That time of it's that time of week again. Sunday, 6 p.m. on the 22nd. And anyway, we're happy to see you all here. Tonight we should have a very interesting presentation by Professor Max Fomitchev-Zamilov. Uh, he's the CEO of Maximus Energy. And in the meantime, let me get some of this homework done here. We want to remind everybody that we still have video on demands available, and it's a one-time fee of $99, and you'll be able to have a copy of all the videos available. So I encourage you all to get signed up for that if you can. If you follow the link on our webpage or this QR code, it'll take you to a page that looks like that, and on here you can order the live feed and all the adjunct interviews they had. Plus, we also have T-shirts for sale, and hopefully we'll be getting some more for next year's. Next year's conference is going to be August 6th to the 10th. I encourage you all to sign up for that, as soon as we make it available, which probably in the next 2 weeks here. We still have DVDs available for those who would like to have DVDs. And I also want to remind everyone we do have a YouTube channel. And the YouTube channel, we have over 1,500 videos. A couple hundred are available for free as subscribers on that. And then the rest are members only. The most controversial stuff will be under the paywall as members only. Because if we don't, what happens is we have have YouTube take it upon themselves to kind of censor us, and they have removed videos from that we've had up there, and they've also taken and they've blacked me out, for a couple weeks at a time. So I encourage you all to get up there, and if you're not a member, become a member. I'm putting up some new videos right now. I'm converting some over to MP4 so I can put them up there. So just keep checking in there, and we'll have more up there soon. And don't forget to give us a thumbs up if you like our presentation tonight and every night. It really helps us with the search engines and everything, and the search algorithms that we get from YouTube. So with that, I'm going to go ahead and switch back to the show, and welcome Max, Dr. Max.
Hi.
And Max was at our conference earlier this year, and put on a tremendous presentation, and I'm hearing from a lot of people how great it was, and so I'm glad he's here tonight, and it will help many of you who could not be there with an introduction into microscopic thermonuclear fusion. And he is, like I said, he's the CEO of Maximus Energy, and we'd like to fill us in with anything else. If you want to know, if we could just delve right into it. There's your presentation.
Okay. Well, Steve, thank you, sir. Thank you very much for having me. And once again, my name is Max Fomitchev-Zamilov. I am the founder of Maximus Energy Corporation, and before I founded this company, I, for many years, was a professor of computer science and engineering at Penn State. And my master's and PhD is in computer engineering and in ultrasonics. So for many years, I wanted to do research in nuclear science, in nuclear energy, alternative energy, and now I have the opportunity to do it. And I'm sitting here in my Florida home, and you see my lab in the background, and you recognize, the picture I used from my presentation, it's the same lab, the same space. This is where I spend most of my time working on the stuff that I love and researching nuclear science. And in the past 5 years or so, I've been working on bubble fusion. And let me see if I can switch the slide. You all heard about bubble fusion. So the general idea is we take a liquid rather. I use oil, mineral oil, and in that liquid, you create bubbles. And those bubbles are supposed to be filled with thermonuclear fuel, like deuterium gas. And when the bubbles expand and then collapse under influence of sound, the temperature inside bubbles rises. And if the conditions are right, you arguably can cause temperature and pressure inside the cores of collapsing bubbles high enough for thermonuclear fusion to take place. So this idea is not particularly controversial. It's been published and discussed and patented. And you probably heard about the Bubblegate scandal. Is when Tally Yarkin of Oak Ridge National Lab published his famous result that he got this reaction to work, and he got to work at Purdue and published some more. But as it often happens in science these days, when funding interests are threatened, infighting begins. So there was a big fight between Tally Yarkin and rival group, and eventually Tally Yarkin was pretty much forbidden from working in this area and having students in this area, because he was found of believe it or not, of guilty of academic misconduct on rather inconsequential trivialities, but that was enough to make his life a living hell. So therefore, this bubble fusion, his bubble fusion research is considered controversial and something that's been published in mainstream scientific journals, but something that has not been established beyond reason of a doubt. And this is what my work is about. The reason I'm working on bubble fusion, the reason I'm interested in cavitation, is I want to establish this as a fact, is a controvertible fact, and devise a recipe that anybody can follow and repeat and arrive at the expected result and confirm that fusion does take place. So this is what I've been working on for the past 4 or 5 years, and of course, that everybody thinks that fusion is going to be the energy of the future. So we hear in the news, in the newspapers, online articles that fusion energy one day is going to power the world, and we keep hearing this every year for 40 years. So despite $400 billion, or who knows how much money governments worldwide spent, there is still not a viable fusion reactor. And the simple reason being, it's a very difficult process. And it's difficult because fusion suffers from instabilities. Be that plasma that's magnetically confined, it doesn't want to stay in this donut shape, doesn't want to stay in place. Or if it's a solid fusion pellet that's being lit up by hundreds of lasers at the National Ignition Facility, it just doesn't want to compress uniformly. Instabilities develop. And trying to overcome those instabilities has been a lot more difficult than anybody is willing to admit. Plasma just doesn't want to stay in one piece, and fusion pellet doesn't want to compress uniformly. And this is what the bulk of the work is focused on. How do we make this process sustainable, and how do we overcome the instabilities? Well, unfortunately, the same principal difficulty exists in bubble fusion. So when you have bubbles, those bubbles are rarely collapse uniformly. We all know that we need to take a bubble of a small size and blow it up to a very large size, precisely 1,000 times of its initial radius. And when you start compressing it, it's very hard to compress it uniformly, especially if you want to have bunch of bubbles, because one bubble is not going to give you enough energy, enough meaningful energy. One single bubble is just a scientific curiosity, but if you have thousands or billions or trillions of bubbles, then you can talk about deriving power from this setup. But then it's impossible to have these bubbles collapse uniformly, and what happens is a jet develops, jet that pierces the bubble, and the bubble falls apart during the final stage of collapse. And that's why to this date nobody has been able to get this process to work. And that's why Telyarkhan's work was initially excitedly received and then viciously criticized, because it's just difficult to make it happen. Well, regardless, sometimes it's best to know enough about, let's say, an idea to be excited about it, but not know too much to where you get bogged down by the impossibility of all of the engineering involved. And that's the situation I was in about 3 years ago when I started this project. So I said, okay, I'm just going to try it and see what happens. So I started experimenting, and little by little, my experimental setup evolved into what you see in this picture. And this is what you see pretty much behind me, except it's evolved since. But I'll have a better picture here. It's a little bit cleaned up, and what you see is my reactor in the middle. So my reactor is a 6-inch stainless vacuum section that's filled up with mineral oil. And the acoustic driver is affixed at the bottom of this reactor, so it's beneath the plywood, so you cannot really see it. But that, piezoelectric driver is powered by a power supply. That's the front, white thingy with the blue screen on this slide. You cannot see it here, but that's what sends the acoustic waves into the oil. And the reactor is about halfway filled. There's this viewport that I use for inspection, and I also use this circulation pump to pass my oil through a venturi that creates the bubbles, and I have a auxiliary cavitation reactor, and then the bubbly oil returns back to the reactor. And behind it is my laser diffraction system for measuring bubble size, diameters. I also have a piezo transducer that is hanging inside to tell me the magnitude of the acoustic waves, and that's the wire that runs to the oscilloscope to read the acoustics. And this is my vacuum system with some pressure gauges. So it's a simplified, cleaned up version of the reactor. And that's how oil looks like. So initially it's a colorless fluid, mineral oil with very low vapor pressure that I also degas and vacuum, to a decent vacuum, because I want to remove all of the air, dissolved air, and all of the other gases that are trapped in it before I introduce my deuterium bubbles. And the reason this oil looks milky or cloudy is because of high concentration of deuterium nanobubbles in it. And on this picture to the right, it's the same oil, but with DTO droplets. So I was experimenting, with bubbles, and I couldn't get bubbles to work, so I started adding, heavy water droplets. And then, when the results started getting more interesting, particularly with heavy water droplets, I was able to increase the acoustic intensity so much to where the viewport glass cracked. So what you see here is actually a catastrophe. The reactor lost its integrity because the viewport cracked, because the constructive interference of shock waves that result from expansion and collapse of water droplets added together and created stupendous sound. It was so strong that it cracked the glass, and that happened more than once. But that was something I was really after. I wanted to boost the magnitude of sound waves, because the thinking was, the stronger the sound, the better the compression. And that's, the schematic of the reactor. So once again, the reactor is in the middle. It's filled up about, half volume with this oil. And that oil has either deuterium bubbles of DTO droplets or titanium deuteride powder. And I'll talk about that, later. And that's the piezo driver at the bottom. And that's my transducer, PCB transducer that I use to read out the acoustics. And how do I know that the reactor does anything? Well, I attach helium-3 tubes. I set up helium-3 tubes next to it, and those are my neutron detectors that are connected to my automated nuclear lab. and I'll talk about that in a moment also. So, once again, when you study fusion science, nuclear fusion, your prime tool for monitoring whether the reactor does anything is in the neutron detectors. So if deuterium does indeed fuse inside the collapsing bubbles or inside the heavy water droplets, then that fusion reaction will generate neutrons, and those neutrons can be detected using neutron detectors. So I chose helium-3 field proportional counter tubes, and if anything I've learned how to measure neutrons, and that's what my specialty is. That's, I would say, even my core competence in neutron detection. And what you're looking here is a bank of 6 helium-3 tubes that I used for a better part of my research. So the more tubes you have, the higher your signal is. And when you start development, your reactor doesn't work. So your neutron signal is non-existent or extremely weak. So you need to have as many detectors as you can to boost the efficiency, so you can pick up the tiniest signal. And once you capture the tiniest signal, you can start looking into conditions that are causing it and kind of start optimizing your reactor from there. So it's far too early in the process to talk about any sort of excess heat being produced by the reactor, but that's the end game anyhow. So the expectation is that at the end of the day, the reactor is going to produce heat. So the liquid inside it is going to get hot enough to where you can replace the oil, let's say, with liquid lithium, because lithium is even better medium for fusion, because lithium-6 captures neutrons that the fusion reactor produces and release additional energy and breeds tritium. So it's kind of common knowledge that you ought to use liquid lithium, and that's what I intend to do at a later stage of this project once I get a better grip on the physics of the process. But that's kind of the end goal here, is to have a system in which the working fluid, be that oil or a liquid lithium, gets hot enough to where it can be passed through heat exchanger, and this extra energy gets harvested, and it boils some heat exchanger fluid that spins the generator, basically. So this is my helium-3 proportional counterbank, and this is the thermal neutron spectrum. So when you use neutron detection, you basically get a pulse that looks like this from the detector. But sometimes you get pulses that are due to noise, and that has been a common problem for nuclear science, because these pulses are very small. They're just a few millivolts, and it's easy to get ground loops or electric noise of the same magnitude. So if you don't know better and you start using radiation detectors, you'll get pulses, all right, but those pulses aren't going to be genuine. And in fact, what would happen in most cases when a novice researcher starts using a nuclear detector, they fire up a generator and the detector starts going off like crazy, and they say, all right, this is working real well. I'm capturing, lots of pulses, but more often than not, they are logging ground loop noise or some other RF interference. So that's why it's important to capture these individual pulses and build a spectrum. And if this detector is working right, the spectrum is going to look like thermal neutron spectrum, and that's what you're looking at here. So if your detector is producing this type of spectrum, and this spectrum is well known to nuclear scientists, you can be sure that what you're counting is neutrons, because if your pulses are noise, they are not going to produce a thermal neutron spectrum. They're going to produce something else. But that's what I was after. And in order to make all of this streamlined, because half of the work is radiation detection, and half of the work is actual research on how to build and operate the reactor, I spent some time in designing hardware and software to automate my nuclear science, and I call it Automated Nuclear Lab. And I make these devices actually, and I sell them to other scientists and engineers, because this is basically a tool for rapid nuclear experimentation. So you want to be able to focus your energy, mental and physical, on actual experiment, and let hardware and software do the measurement work for you. And that's what I've spent a few years developing. So this hardware produces high voltage to power the detector, and various inputs here. You can plug in your detectors and you can record their signals, log their signals. This is the software that I developed, and this is the software that called Pulse Counter Pro. That's essential workhorse of all of my nuclear science research. And I'm happy to see that more and more scientists use this software now, like folks at MIT, Texas Tech, Purdue, Hong University, started using my hardware and software in their research, because it gives you everything you want to know about what your detectors are actually detecting. You can see the individual pulses, you can see the count rate history, you can see the spectrum, and you can run the statistical analysis. This is rather technical stuff, but it's important to remember that whenever you do an experiment, and be that nuclear science, or you build an engine, or you build a reactor or something else, measurement is everything. So unless you master the measurement technique, unless you learn about and control the systematic sources of systematic error, you cannot make any claims about what your system does. So if you take a single measurement, it's meaningless. It's only when you understand your measurement device, when you understand what can go wrong, how this measurement is acquired, what are the sources of errors, meaning what factors contribute to correct or incorrect readings, what factors influence the readings. You cannot pass any judgment on whether your device is doing anything. And unfortunately, not enough people are taking the effort to learn the measurement. And if anything I've learned in my career as a scientist, measurement is everything. So in this case, this automated nuclear lab, coupled with Pulse Counter Pro software, automates the measurement process to where I don't need to worry about it. I capture enough data to where at the end of the day I can go through my data and I can tell how many neutrons I counted, if those are actual neutrons or not, or if that was noise. And I can run countless experiments. In fact, the reactor you see on the background, I was operating it today. I was running a bunch of tests, maybe 100 tests I was able to run with it, and I used my hardware and my software. And what is also important to know is when you deal with nuclear science, you're dealing with random processes. And that's what I'm trying to illustrate with this slide. So if you take a singular measurement with a nuclear instrument, you can get any value. Like bars here, they represent individual measurements. So this measurement resulted in 7 neutrons, this resulted in 17, and this resulted at 0. So that's what a random process means. So whenever you take any nuclear detector and you run any nuclear reactor or any nuclear experiment, and you measure anything, you get a random number. So if you take one measurement, it doesn't mean shit. It could be 0, it could be a million, it could be a trillion, it could be 10. It doesn't mean anything. So you need to run a bunch of measurements. And as you run these measurements, they need to form a distribution. And you heard about normal distribution, but when you use radiation counters, the distribution actually has a Poisson shape. So all of these individual measurements that you take, they need to form a Poisson distribution, and that's what this envelope shows. So red bars are corresponding to the background counts, and blue bars correspond to the counts from the experiment. So translating this, basically red bars are controls. So the reactor is turned off, and blue bars are measurements when the reactor is turned on. And because we're not talking about a Chernobyl-sized reactor, we're talking about an experimental reactor that I'm researching. I'm trying to get it to work. It doesn't work too well, so it produces very few neutrons above background. And the only way you can determine that is by running a bunch of control experiments, basically sampling your background, building a Poisson distribution, then capturing a bunch of measurements when the reactor is active, and building another Poisson distribution, and then running a statistical analysis. And that statistical analysis is called student t-test. And at the end of the day, it produces a p-value, and that p-value tells you what are the chances that these two curves actually is the same curve. And it's a metric that every scientist uses, every scientist understands, and what you're looking for is a p-value less than 5%, meaning that there is only 5% chance that these two curves is in fact the same curve, and 95% chance that these two curves are actually different. So this is a standard practice in nuclear science and in medicine anywhere, where you have two sets of measurements that deviate from each other ever so slightly. You need to do this statistical analysis, and once again, my software does it. And this is how a typical run of, let's say, day worth of experiments it looks like. So every bar here is a measurement. So every red bar is a background measurement. So I captured 24 background measurements. Then I turned on my reactor and I captured these blue measurements. And this line is a p-value trend. So p-value trend approaching 0 is actually telling me that neutrons from the reactor overpower the background neutrons. And that's why I'm happy to see this. I turned off the reactor. I captured 3 more background measurements, and I see they're kind of lower, but they're not that lower, so you cannot really tell without statistical analysis. I turn my reactor again, and I see that my p-value is approaching 0, and you can see here. So I captured some more background, run some more experiments, and the more you do this, if your reactor is in fact producing anything when it's operational, this p-value needs to approach 0. So this is a very good day of work. I see that background is consistently lower than the reactor neutron flux, and the software tells me that my neutron flux is about 40%. I cannot quite read the print, but I think 40% above background. So that tells me that I'm on the right track. So whatever I'm doing, is good, and I use the data to optimize my reactor performance. But this is, how my acoustic sound looks like. So my, for the better part of my experiments, I used 20 kilohertz sine wave to excite, the bubbles inside the reactor. But once I started introducing droplets, I started experiencing these massive spikes. So those spikes are interesting. They're far in excess of what you see, the acoustic excitation of the piezoelectric driver. And I think those originate from the constructive interference of individual bubbles expanding and collapsing. So when bubbles collapse, they rebound, and when they rebound, they launch outgoing shock waves that constructively interfere. That's, I speculate, the source of the spikes is, and these spikes are several atmospheres, several thousand atmospheres. So maybe my driving pressure is 3 or 4 atmospheres, but this spikes is several thousand times stronger, and they were strong enough to break the glass. And that's when the magic started happening. So when I started this work, I expected that I'm going to get my reactor to perform on bubbles, but that didn't happen. So I added some water droplets, and nothing happened. So I added some titanium deuteride powder to the reactor. Nothing happened. Then I added titanium deuteride with water droplets, and then I saw this neutron flux. And if you look here, it says 1500 counts per minute. So background is like 30 or 20 counts per minute. So this flux is like 100 times in excess of background. So it's so strong to where you don't even need to do the statistical analysis. So once I saw that, this was a truly massive neutron signal, I was really, surprised and happy, because it told me that, finally, there was a success. Finally, my reactor was started doing something, and the neutron signal was so strong, it was 100 times in excess of background. So I recorded, what my neutron detectors produced, and, this is a signal. And each spike here is a legitimate neutron event. So if I zoom in, I can in fact see that those are, good, neutron pulses. So I zoomed in, and, each vertical line is individual pulse, but this little bunch of undulations is in fact noise. So that noise is fortunate. I was fortunate that noise appeared here. So it was due to capacitive coupling between the detector bank and the piezo driver affixed to the reactor. So fortunately, this noise was small enough to where it didn't affect, the software. Software was able to cope with small amount of noise. But it was good for illustrative purposes, because I see that neutrons happen only when the acoustic is on. So when the sound is on, I see neutron pulses, and when there is no sound in between of these undulations, there are no neutrons. So it is telling me that neutrons originate, from events associated with cavitation, due to acoustic excitation of the working fluid in the reactor. So I was very happy to see it, and that's another run that tells you So this is what I captured overnight. So I ran background counts overnight. And you see here is count rate per second. So it's hardly, it's less than 1 neutron per minute. And then I turn the reactor on and immediately, counts build up above background. I turn it off, returns to background, I turn it on, and counts keep increasing. So one thing I noticed, the longer my reactor operated, the higher the counts have gotten. So basically, after I detected this in a massive neutron flux, it was about 3 years ago now. I spent the next 6 months trying to research not so much the reactor operation, but trying to prove to myself that the neutrons I measured were in fact neutrons. Because if you want to claim something as unusual as bubble fusion, first order of business is you got to show that your measurements are correct. So it took me 6 months to overcome the burden of proof and show that my measurements are correct. And by the way, in some cases there were even multiple neutron events, like this one. You see 1, 2, 3, 4 neutrons spaced up so closely together they cannot even be resolved. But my goal was to run the reactor for an extended period of time, like for 1 hour, and to capture a neutron spectrum and to show that neutron spectrum was in fact a thermal neutron spectrum. And that took me almost 4 months to accomplish. But once I was able to do that, I knew that my signal wasn't due to noise. My signal wasn't due to capacitive coupling, which took some time to get rid of. So my signal wasn't due to acoustic interference or thermal interference on the detectors. And I used different kinds of detectors. But in the end of the day, I was able to capture this beautiful thermal neutron spectrum, and that was sufficient to actually publish the results. So I set off to publish a paper, and that paper was finally accepted for publication in May of this year. And that's why I started actually talking about my work, because up to that point I wasn't sure if my results were good enough. But once my paper was peer reviewed by my fellow scientists and was published in Nature Scientific Reports, that convinced me that I should actually share what I've learned. Yeah, and here is the inexplicable result that I actually did not include in my paper because I don't understand it. And if you recall the slide here, this is what I like seeing. I like seeing neutrons that come in when the sound is on, and when you turn off the sound, the neutrons should be gone. But this particular chart is telling something else. So I start the reactor and you see these red bars building. And when I turned the reactor off, I expected the counts return to background instantly, but this didn't happen. Instead, you see this gradual decline. I turn the reactor on again, and neutron counts gradually build up, and you see it's now higher than before. I turn it off, and once again, it doesn't turn off instantly. It takes a while, like 30 minutes, to relax the background. And it was happening over and over again, and I couldn't wrap my head around it. I thought, how is it possible that my neutrons keep coming when I turned off the reactor? There is nothing to excite the bubbles. So what does it mean? Well, I don't know what it means, but it means that the process that gave birth to these neutrons isn't bubble fusion, because bubbles weren't expanding or collapsing when the sound was off. Or if they kept expanding and collapsing when the sound was off, there is some weird process that's happening within the reactor that generates sound. But I don't recall seeing sound on my piezoelectric transducer that I used to listen to sound when the sound was turned off. So it's telling me that some interesting physics is happening there, and it's not at all physics that I expected to see, and it's not physics that we understand, and it's the physics I'm trying to research. And maybe that's why I'm having a lot of difficulties trying to replicate my experimental findings. I was able to reproduce my reactor operation for many times. I was able to operate my reactor for about 6 months. And part of it was that I mixed, this working fluid that you see here on this slide. Let me go back to it. Yeah, this is my working fluid. I basically mixed it by accident. So when I was mixing my working fluid on purpose, the reactor never worked. And I dumped that fluid, that oil, into a waste bucket. And one day I just didn't want to use fresh oil anymore because I was running low or I ran out. So I took oil from the waste bucket that had a sum of all of my failed experiments with a bunch of admixtures, with bubbles, with droplets, with titanium deuteride powder, and that's what I used. And that's when I've gotten my results. So as it often happens in science, the discovery is accidental, and it was accidental in my case. And I was able to use this working fluid for 6 months and collect a bunch of data, hundreds of successful test runs, these inexplicable results. But when I ran out of that working fluid, my reactor quit working. And ever since, I couldn't mix it again. So I tried doing it on purpose. And for 3 years, I tried, and I couldn't. Yeah, and I think the reason I couldn't is because I was trying to use conventional ideas about how fusion should work. So now I'm trying to unlearn everything I learned about fusion, because that's the preconception that drives how you set your experiment up. And because that was unsuccessful, I really need to unlearn everything I know about fusion and leverage the creative side of me and just experiment without thinking and see where intuition takes me. And that's what I'm trying to do now. So I'll tell you more about what I've learned. So this is what I think I know. So I mixed this perfect working fluid by accident. The oil initially was clear, but it's gotten heavily oxidized, and you can see the change in color. It's yellowish and it's greenish. So the green hue probably comes from the copper soap that developed inside the reactor because it uses copper gaskets to connect the vacuum sections. And the oil could have contained some borax too, because you see these borax boxes in the background. I use them to screen background radiation, or for that matter, the reactor radiation. And those boxes were leaking, so some of the borax could have found its way into the waste bucket for sure. And oil definitely contained D2O droplets, because I experimented a lot with D2O, and it definitely contained deuterated titanium particles in it, possibly some deuterium bubbles, definitely some small amount of deuterated hexadecane D40, which is just a deuterated oil. And there was some xenon, but I eventually evacuated xenon gas. I was trying to replicate, to test Sputerman's idea, where he thought that a mixture of xenon will promote the shockwave formation. I really liked that idea, so I tried xenon, but I ended up evacuating it, so I don't think there was any xenon left. But anyhow, another interesting thing, that the oil got really electrified when I was pumping it. So if you recall my blue pump, and I used Teflon tubes in some cases, and oil is dielectric, Teflon is dielectric. When you rub two dielectrics together, you get static charge. So the oil was so charged that occasionally a spark, like a 20-inch spark, would jump across the outer surface of the Teflon tube. So that's a lot of potential. And the oil was curved inside of the reactor when I was pumping, meaning it's not a flat surface, it's a curved surface, because there was so much static charge. So it's possible that some of the bubbles or droplets, acquired and kept that significant electrostatic charge. I also experimented, with various pressures, and I was able to produce neutrons in a wide range of pressures, from low-grade vacuum of 4 torrs to ambient, which is 760 torrs. But most of my experiments were in the 4 to 20 torr range. It's because when I was researching it, I figured a way to get my reactor to work consistently. And the way it worked, I would basically evacuate and clean oil inside the reactor, and then add 1 milliliter of oil from the waste bucket into it. And once I did, the reactor would start producing neutrons consistently, and that's allowed me like a repeatable set of experimental conditions that I was studying. And usually, the oil was clear and the pressure was just a few torr, and I would introduce this 1 milliliter of oil from the waste bucket through an injection valve, and then the reactor would start producing neutrons. But during my first experiment, the oil, was opaque. It had so many bubbles and so many droplets that it was still working. So maybe that wasn't important. But this process was repeatable and sustainable for months. So emulsion lasted for about 6 months, and at the end of 6 months, unfortunately, it separated, and part of the suspension dropped out, and that's when it quit working. So what I don't know, as I said, I don't know if my neutrons were from fusion. In order to establish that your neutrons are from fusion, one has to either measure the energy of those neutrons, and this means engaging in neutron spectroscopy, or you measure daughter products such as tritium. So if I was able to measure tritium, I would be able to say, yeah, that was thermonuclear fusion. But I didn't get to it. I was so preoccupied with just being fascinated that my reactor worked, and I was so preoccupied with measuring neutrons that I didn't get to measure tritium, because, as I said, measurement of anything is a thing. So to learn how to measure tritium in small concentrations is probably a 6-month project. So unfortunately, I didn't get to do it, because I ran out of my emulsion. So I don't know if the reaction took place in the bulk or on the surface. So maybe, those were the bubbles trapped on the surface, maybe on the bottom flange of the reactor, or maybe on the sidewalls. So frankly, I don't know. Let's see, what else I don't know. I don't know why neutron signal was gradually increasing in time. On one hand, this increase is supportive of the thermonuclear fusion idea, because when you start with pure deuterium, probability of reaction is low. But as you get more and more fusion reactions, you start breeding tritium, and deuterium-tritium reaction is a lot more likely. So the second your deuterium fusion starts to work, you start getting tritium, and tritium is a lot more likely to react with deuterium. So yeah, you'll get more fusion reactions because of it. So this gradual increase of neutron counts with time is consistent with the idea that it was thermonuclear fusion, because then you produce tritium, and tritium drives the reaction rate up. But I don't understand how this neutron signal could remain on when I turned off the sound. So this is not compatible with thermonuclear fusion idea, because without bubbles expanding or collapsing, there's nothing to drive the reaction. So unless somehow sound remained on, or something else, some other process remained on that drove these bubbles even when the piezoelectric driver was turned off, I cannot explain this. But I got to be honest about my findings. So that's what I'm telling you. That's what I observed, and this is what I tried. So I tried for 3 years now to replicate this magical mixture without success. And part of that reason was, I was too hung up on certain ideas. Like 1 year I spent on being hung up on the idea that D2O did the trick. And I worked, with various concentrations of D2O and various droplet sizes, no luck. Then I thought, well, what did I overlook? Well, I overlooked titanium deuteride. So I got this idea that it was the titanium deuteride. So I spent another year on just that. No success. And then I realized that maybe it wasn't, one of these things, that maybe, it's a synergistic action. But I also tried a bunch of surfactants to modify, the surface tension and to modify the stability of bubbles and droplets. Not so much. I have tried charging oil electrostatically, and this is something I'm exploring, now. This is something I underexplored. So this is very much on my to-do list. But if anything I've learned in this 3-year process, I've learned how to build this stupendous acoustic pulses. So this I can do anytime now. So I think I get a good handle on it. So what I need to do is I need to inject a bunch of bubbles or powder or water droplets. And, with some manipulation within the reactor, I can get these pulses to show up. So at least, I got half of the mystery of the table. I know how to get my acoustic signature to match. But I haven't gotten the working mixture right yet. Colleagues of mine encouraged me to apply for a couple of grants. The Department of Energy had a couple of solicitations for fusion energy, like creative approach to fusion. And it's a funny thing when government asks you to come up with something new, they're not really asking you to come up with something new, because this is what I did, and I submitted those proposals, and they got rejected. So the last rejection came in last week, and it means translating from the government speak to common speak. When they're asking for something new, they're basically asking for a new increment to something they're already doing that doesn't work. So that's what new means to them. So they are running this large reactor that doesn't work. So they're asking for new ideas, and it doesn't mean they're asking for ideas on how to make a new reactor. They're asking for new ideas how to tweak their reactor to make it work. And that's not what I propose. So my bubble fusion or microscopic thermonuclear fusion idea is too far off from what government is interested in. So they didn't pitch in any money. So it's sort of irrelevant asking the question what needs to be done, because in order to do this task, you really need to hire somebody to do CFD modeling. You need to buy a high-speed camera to actually look at the bubbles and validate the model, and you need to build a nanodroplet nanobubble generator and hire a technician to run it. I don't have time, money, or patience for it. So that's why professors apply for grants, because once they get a grant, you can have actually a postdoc or two, working for you, a grad student, and you can tell them, okay, write this modeling program, run this a bunch of really boring, mundane experiments. But because they need the scholarship and they need to graduate, they do this kind of work. But if you are to do this yourself, you drive yourself crazy. So I said, screw this. If I have the money, I can hire somebody to do it. But that's too boring for me to do. So I need to try something more creative. So what I'm thinking now is I'm definitely thinking that titanium deuteride is crucial, because I never had neutrons without that powder being present in my oil. I think that static charges are probably important. I need to explore them more. And I'm thinking that my fusion was happening within the bulk of titanium deuteride particles suspended in oil. So I think the cavitation bubbles were expanding and collapsing, and these cavitation jets were impinging onto solid titanium deuteride particles, and fusion was occurring inside the particles. So this is what I'm trying now, and the experiment you see in the background is devoted, to testing this idea. So the oil I'm using now, has a bunch of titanium deuteride in it. And let's see, do I have a slide for it? Let's see. How come there is no picture here? Okay, so dang, I thought I had a picture about it, but maybe not. I apologize for it. So I decided to create my own titanium deuteride powder, and that's what you see not so clearly in the back. What you can't really see is a cylinder that looks like this, that has a titanium sponge. And around that cylinder, there is a heater, and to that cylinder, I connected a deuterium lecture bottle. And when you start heating up titanium sponge, once the temperature approaches 350 centigrade, that sponge starts absorbing deuterium like no tomorrow. So, for example, a pound of titanium sponge, in my case, absorbed 5 of these lecture bottles. So I spent like $5,000 on just titanium gas being absorbed by this titanium sponge to formulate titanium deuteride of my own making, meaning of known purity, of known molar composition. And that's the powder I am using in my experiments, because the powder I used before was made by something else. It wasn't particularly high grade. It was electrochemically loaded, so I didn't know the exact deuterium fraction. So I figured, well, I should make my own powder. And I had a picture of it here, so I even placed some on eBay for other researchers to try. And it kind of looks like this. So that's the powder that somebody else made for me. So I made my own powder, which I think is better. And I thought, what if I just focus on this powder and maybe forget about cavitation per se. So I took some of this powder and put it in this pestle, and then I installed this ultrasonic driver over it. And this is just a titanium horn to which a piezoelectric driver is mounted. And I thought, if I just compress this powder in this pestle, so maybe I'll get neutrons from it. And that is what I sort of observed here. So this is my background count, and this is my experiment count, and these are my background counts. And it looked encouraging, but it's not a particularly reproducible result, because when you're working, with solid powder in a pestle, so your driver gets stuck. It pretty much gets stuck and welds itself, through this powder to the sides. So this driver no longer, vibrates or compresses the powder. And I tried like a bunch of modifications of this idea, where I was trying just to pound on dry powder with this ultrasonic driver. And I could never get it to perform consistently. Either the powder gets expelled, or it gets stuck, or something else happens. So I thought the results were interesting, but I just couldn't make anything reproducible out of it. So I thought, well, I should try to continue working with titanium deuteride powder suspended in oil, and maybe even make of the bottom plate of my reactor out of titanium, and deuterate the surface, and also roughen the surface somewhat, like with sandblasting, and then have this cavitation bubbles impinge on the surface and maybe produce neutrons in that way. And I was trying to get a machine shop to make this titanium flange for me for 3 months now, or 4 months now. They haven't made this plate yet, so I wasn't able to run this experiment. But that's one of the things I want to try, and that's one of the limitations of being like a small researcher, in the sense that you don't have control over other folks. You need to get your parts done. Everybody is busy, so nobody is really keen taking small jobs, or few people know how to work titanium without destroying it. And I conceived this idea like 4 months ago, and still I don't have the parts. So I'm at the mercy of a machine shop, whether they're going to make it to me or not. But in the meantime, I have this titanium deuteride powder that I keep working with in my reactor, and hopefully I'll get somewhere with it. So alternative theories that I'm trying to pursue is what if this electrostatic charge is supremely important? So these bubbles or droplets, they will capture the charge on their surface, and this is extremely well-known process. In fact, the suspension or emulsion stays suspended or emulsified is because a lot of these droplets or particles carry electrostatic charge, and they repel one another, and that's why we get a suspension. So I remember that way back when Smorodov, my compatriot from Russia, published a paper where he started glycerin bubbles. Glycerin is a polar liquid, meaning that the surface will be electrically charged. So when this bubble collapses, it doesn't quite collapse all the way, but high charge concentration builds up, and that charge can potentially arc over through the bubble. And if I could get this to happen in my case, maybe I don't need for bubbles to collapse all the way. Maybe I just need bubbles to capture a lot of charge, and then have them collapse enough to where that charge concentrates really, really strongly, and the arc develops through the bubble, and maybe that arc is going to promote thermonuclear fusion within the gas. So that's one of the ideas I want to pursue also. In this illustration is a colleague of mine also ran an experiment in Russia many years ago, and what you see here is glow, and this is a nozzle, and this vacuum section is filled with oil, and there is a high pressure pump that feeds this oil through this nozzle, and when the oil exits the nozzle, this electrostatic friction takes place, and oil starts to glow rather strongly. So plasma develops in liquid oil due to friction, and that's, I think, a pretty cool, pretty amazing experiment. And in their case, there were no bubbles or droplets in oil. Oil was not deuterated. So that's one of those experiments I want to run, except that I'm a little wary to run it in my house, because on more than one occasion oil leaked and sprayed all over the place. So if I am to boost pressure, I definitely don't want to do it in my home lab, because of safety considerations. That's why I'm kind of keen to move this research project to the next stage. So after I published my Nature Scientific Reports paper, a bunch of people approached me and said, hey, why don't you try to take this project to the next stage? And I said, well, I don't know how. And they said, well, try crowdfunding. And luckily, U.S. government has passed Reg CF regulation crowdfunding to where you can raise money into a startup company through crowdfunding process. And that's what I've done. I've registered at the WeFunder, and I created the Maximus Energy link, and I basically solicit public investment into Maximus Energy Corporation, which is my company. And this company doesn't just do research. This is actually a profitable business that manufactures and repairs scientific equipment. And I repair and remanufacture all sorts of nuclear detectors, vacuum pumps, and gas analyzers, and even electron microscopes for other researchers to use. And that's how I'm able to support myself, derive an income, and have enough money left over to do the research. So if you will be, joining Maximus Energy, you will be joining a profitable company, and the goal is to raise about $500,000 to where I could hire an assistant and move this, what you see on the background, into a lab, to where we can work on, with this assistant, with this technician / engineer, on a bit more interesting experiments that at least require 2 people for safety concerns, like this high pressure oil, or experiments with liquid lithium, which is not safe, to do at your home. So that's what I really would like the next step for me in this project to be, to where I can move this out of my house into a rented commercial space and hire a full-time research assistant to work with me, so this research could go higher, could go faster. And if you want to read more about my work and what I do, obviously I recommend that you read my observation of neutron emission paper that was published in Nature Scientific Reports. And I've published additional papers hosted on my website about, principles of neutron detection, about, how my automated nuclear lab hardware works. This is all disclosed, all in public domain, so you can build your own system. I even describe how my software works. So you don't have to buy my system, don't have to use my software. You can build your own, and you can write your own software, but it will save time, if you buy the tools that I make. That way you don't have to spend effort on it. But that's all I have to share. So thank you very much for your time. So if you really want to help this project, I guess 2 things you can do. If you're a researcher, you can buy, my hardware and software, or if you're interested in seeing new energy developed by a company and being shared with everyone, you can join me on WeFunder, and that way, hopefully, we can keep this energy out of hands of large corporations and government, so everybody could use it. And that's why, people who already joined, committed whatever money they could, because they want to see that happen. So once again, thank you very much.
So I'm speechless. So it almost looks like you almost like a spark gap at that last piece of equipment you had.
Mm-hmm.
Yeah.
You mean this where the spark was running through oil?
Yeah.
Yeah, that's a fascinating experiment. Ever since I learned about it, I wanted to do it, but as I said, it's not safe to work with high pressure oil at home, because if it spills, it's going to be a mess, and this place is already a mess. And you need someone, like I'm saying, when you work with high pressures, high voltages, you need a second person to pull the breaker, or drag your body out of the pathway of hot oil stream, or out of wires, and that stops me from a lot of from running some of more interesting experiments, because there is nobody that could stand next to me with a fire extinguisher should shit hit the fan. But that's why I decided to do a WeFunder campaign, so I could hire a technician to work with me full time. So that's,
well, if you send me an email with that address, I'll post it on the description part of the
yeah, I'll do that.
This will be up there forever.
Mm-hmm. Thank you.
And anyway, does anyone have any questions here? So I guess the goal here is just to get something that will cause enough heat where you can heat up more water, or
Yes, yes.
another.
So the goal is to produce enough fusion reactions to where the working fluid gets hot, and then you can run it through heat exchanger, and then the heat exchanger can power a generator. So at the end of the day, the working fluid needs to get hot. So, and the reason I'm using oil is because it's easy to work with. So eventually, it needs to be liquid lithium. So, and that's what I'm really keen on trying. But as I said, I don't want to do it at my home, because if lithium catches fire, then I'll have a big problem on my hands. So best to do it somewhere else. But that's one of the next steps in this process. We need to switch from working with oil to working with lithium, and I have a bunch of lithium. So I have about a gallon of lithium that I bought a while back that I want to fill my reactor with. It's just I really need to hire somebody to help me with that research, and not so much just a technician, basically, or a lab assistant.
Here's a question for you. What are the 3 types of time you mentioned during the conference in August?
Oh, yeah. So I think, broadly speaking, there are 3 types of time. One is, biological time. The other is chemical time, and the third one is nuclear time. So we'll start with chemical time. It's very easy to understand. Temperature drives the rate of chemical time. The higher the temperature, the faster chemical reactions go, right? And each of us have a time machine at their home. It's a refrigerator. You put something in the fridge, temperature goes down, chemical reactions slow down. That's how we can cheat and keep, let's say, produce fresh, because we slow down chemical time. You heat, chemical time goes faster, chemical reactions go faster. You cool, chemical time slows down, chemical reactions go slower. But chemical time does not affect nuclear time. So nuclear decay rates aren't affected by temperature. It's a very well-known fact. But we know that quantum mechanics drives quantum processes. So therefore, in principle, it should be possible to affect the decay rate of unstable radioactive isotopes if we can figure out a way to control nuclear time. And that's one of my research goals and one of my dreams. I have run a bunch of experiments where I hypothesized what can control the rate of nuclear time. And one of the hypotheses is very strong electric field, or very high electrostatic potential, or very high charge concentration could affect the rate of nuclear decay, of natural nuclear decay, meaning the rate of nuclear time. So I run several experiments with no results so far, but I have by no means exhausted that line of research. I need to run a bit more experiments, because if you can control the rate of nuclear time, forget about fusion, because then you can just accelerate the rate of natural decay, let's say of thorium or uranium, and then you can harvest unlimited energy, thermal energy, just from let's say a chunk of thorium or chunk of uranium. Normally they decay very, very slowly. Half-life is like several billion years, but if you accelerate the rate of decay by controlling the rate of nuclear time, then you can release that energy on demand. And that is sort of what happens in a conventional nuclear reactor, with the help of chain reaction. So chain reaction accelerates the decay. Well, it's an incorrect statement, but chain reaction results in fission, right? Not so much accelerates the rate of natural decay, which it doesn't. But if you could accelerate nuclear time, then you can accelerate off the rate of natural decay. Then you don't need fission. So that's what I'm really interested in. And of course, the third time is biological time. So biological systems, their lifespan is determined by so many things, and their sense of time, how we perceive time, is determined by something else that isn't coupled from chemistry. Be that in part metabolic reaction is chemical, but at the same time it's not entirely chemical. So there is another level of complexity there. That's why I put biological time in a separate category. So it's a time of very complex systems, in other words. And then we have chemical time, and then we have nuclear time. That's my thinking.
So, well, how hot have you been able to get something using your technique?
How hot?
Yeah.
Um,
Or did
I
you
don't
let?
know. I mean, I don't really measure temperature right now. I'm really focused on measuring radiation. That's all I really measure at this stage. And in my experiments on accelerating, the rate of nuclear decay, I was measuring the rates of nuclear decay of samples that I exposed, let's say, to high electrostatic potentials or high electric fields. I measured it, before and after to see if there was a change. And so far, I haven't detected any, but I barely scratched the surface.
Well, here you go. Ever try frequency signaling?
I don't know what that means. They have to elaborate. But I see a question about borax boxes. So borax boxes are for screening background radiation and for screening a reactor radiation. So in my previous work, when I was working with X-rays, I used lead bricks to screen myself from X-rays, and I didn't use enough of them. So I've developed some, health issues because of prolonged exposure, to kilowatts of X-rays. So this time around, I'm taking no chances. So I align my reactor with borax to screen all of the neutrons that can originate from it, and also to protect the detectors from background neutrons and increase my signal to noise ratio.
Well, is that better than lead?
Well, it's better for neutrons. For gammas, lead is better, but this reactor is not producing so much gammas. It's mostly producing neutrons. So I'm not using lead. I'm using either borax or HDPE or water or paraffin. Any of that works, but borax was conveniently sold in boxes, that I can use as bricks, and because it has a lot of boron. So boron is really, the substance that captures neutrons.
So, where do you get this borax?
Walmart. So I bought it at Walmart. So I bought all the borax I could buy at Walmart, and your scientific, not your typical science supply story, but it works.
Walmart's good for a lot of stuff.
Mm-hmm.
Yeah, it's underrated sometimes.
Yes.
So, and have you worked with these rotating cavitators?
Rotating cavitators, yes. In fact, that's where I started initially. About 10 years ago, I used to have a company in Pennsylvania called Quantum Potential Corporation. And at the time, we wanted to pursue bubble fusion, or cavitation-induced fusion, using these big machines with rotors and stators that produced hydrodynamic cavitation. And unfortunately, we quickly ran out of money because building those machines were expensive. Each of them required 100 horsepower motor and lots of fluid. So we had to retool, and I retooled that technology towards heavy oil upgrading, and I succeeded reducing viscosity of heavy crude oil. And we were about to license our technology to Shell, and then the oil price crashed in 2015. The oil price went from $200 per barrel to $50, and that wiped out all of our customers, and we had to close down the company. But that was, my experience with this hydrodynamic cavitation machines, and now I'm not pursuing that anymore because it's difficult to work with. Let's say in a home lab. So I'm using the smaller reactors that are cheaper, easier to make, and easier to control.
Well, I was reading that about 30, 40 years ago. There's a book out called Breakthrough Energy.
Mm-hmm.
And I believe it's out of print. I can't find it anymore. I think I might even have a copy laying around somewhere. Written by Dan Davidson. Have you read his work?
No, that doesn't sound familiar.
Because he was doing telling them how this guy was working with an acoustic setup like you have.
Yeah.
When they were trying to break up water, and there was a certain frequency they hit, and it put a hole through the ceiling. Because of its association so far. So
I know someone in Florida who is doing similar research with cavitating water. They're actually using my equipment, and occasionally I help them with advice. And they have some interesting results. I was able to see their setup, but I don't pretend to understand what they're doing. And that's kind of my point. we need to forget pretty much everything we know in order to discover something new, because it's our knowledge that's in the way of discovery. And in my case, that's exactly what's holding me back. So on one hand, knowledge helps you to get ahead. On the other hand, it's holding you back because it's steering you towards certain ideas or certain pathways. And I think if we're discovering anything, it would be some random experiment by some crazy amateur in a garage who tries something, and eventually I hope that that individual gets paired with someone like me who can actually research the process and establish why does it work. First of all, show that it works, and then researches with scientific rigor and accuracy to actually establish that something new is happening. And I think that's a magical let's say mixture, when you have an enthusiast, an amateur who is inspired, and you have a scientist who actually knows how to do research. You sort of need both. So I kind of have to play both roles in my own research, but I'm more often more scientist than let's say inspired amateur, and that could be let's say a detriment at times because scientists telling you know how things work, right? And then you try them and you don't get the result. And the amateur says, well, I don't know how things work, so I'm going to try this and maybe it will work. And scientist says, this is stupid, but that's exactly how the discoveries are made. You try something stupid, and one day you realize that you're stupid because you thought you know everything, but you don't.
Well, if you send me that information on the refund thing, and I'll post it on the.
Yeah, I think I just did. So
okay, and I'll look at it later on tonight. And with that, I'm going to call it a night. And thank you for being here, and thank you for coming to that conference. And for those of you who haven't seen it, we do have the 2024 available as DVDs, or we also have it online through HowTube. If you just go to my website and click on the DVD thing, that'll bring it up. But thank you again, Dr. Max. And
well, thank you for having me.
And you got some supporters out there in the comments and that, and they're all
very good. Thank you, guys. Take care. Bye-bye.
So, okay, I'll talk to you later. And oops, stream.